So Sebastian Lutter will talk about skylift safety. Sebastian Lutter is AI engineer and CTO at Pixolution, which is a small company in Berlin where they mostly work on computer vision projects and also on premise solutions. So Sebastian Lutter has been in the computer vision community for quite a while. So he did his master in computer science already in 2011 and has been working with computer vision already since before the deep learning hype. And I'm actually very curious to hear. So they seem to work with quite wide range of different projects about classifying fonts in images or visual search, and also about anomaly detection in videos, which will be the topic of this video, where it's going to be about how to improve skylift safety. I think also, yeah, unfortunately, a recent topic again. And yeah, I think the stage is yours, Sebastian.
Thank you very much for this warm welcome. Yeah, hello, I'm Sebastian, and today I'm talking about solving a key surveillance system problem by using action recognition and anomaly detection models. And yeah, I'm an AI engineer, software architect, and team lead since the last decade. And I strongly support the idea of ethical AI and do and talk a lot about the social impact of AI. So yes, I work for Pixolution. We are a small team of experts, a self-funded company from Berlin. And we basically provide a visual search engine called Pixolution Flow as a product. And we do custom AI projects and consulting centered around image and video data. The use case I will present today is the use case of one of our clients, the company Pixis AI from Colorado, USA. And they provide an AI-based real-time machine surveillance system that is built upon an anomaly detection and action recognition model. I'm responsible for the model architecture and help to build the system architecture. The product itself is an offline box with a camera. It is placed at every lift load and unload location. It is directly connected to the lift control system, and it is able to slow down or stop the lift in dangerous situations. And like any other AI project, it starts with the collecting and the preparing of the data. It's always a huge part of a project. And the Pixis AI team placed 35 cameras at 9 different ski resorts and collected around 10,000 hours of video footage over several months. They created some labeled data that can be used as a ground truth or for supervised training, but most of the data is unlabeled due to the huge amount of the data. And we are interested to identify 13 action classes that are used to decide if and what directive the system should send to the lift control system. So what else can we say about the data? The footage is taken from different angles. We have different scenes. They all have in common that they have a static background, and that the information itself that we are after is not only spatial, so not only shape and location, but also temporal encoded. So it's the motion of things through time that we are interested in. We have different kind of scenes. We have, for example, simple scenes like this. There's not much going on, no crowded people, no complex behavior patterns. And the definition of anomaly is quite obvious here. Someone is falling down, and the model can learn what is normal and later on should identify anomalies by using some kind of reconstruction error. There are only two cases. There is a problem or there's no problem, so we have a binary detection for the simple scenes. And we have complex scenes like this. It is a load and unload situation. A lot is going on. Complex behavior patterns are there that we need to distinguish. And we have different actions depending on the action classes. So we have load and unload problems or potential problems like this one. And there are normal activities and also noise or bad weather situations. To solve these two cases, we will use two different models. We will use an anomaly detection and an action recognition model. What they both have in common is that we need a self-supervised architecture because labeling is expensive and the huge amount of data simply does not allow to label all the data. And also sometimes it is not the best option. Self-supervised training can be superior because it defines the pattern itself. And sometimes the pattern it founds is much better than the label a human would provide. And also important, we build a near real-time system. The model needs to be lightweight enough to run on some Intel box at the load and unload location. First, we'll look at the anomaly detection model. This is a self-supervised trained model which uses the generator and discriminator pattern to supervise the training. As an auto generator, we use an UNet, and the training goal is to predict a future frame because we work with sequences and we want to focus the model on the temporal aspect. Usually, UNets are used for image segmentation, but you can use them for predicting future frames as well. Since we are after the temporal aspects of the data, we included an optical flow loss. An optical flow image is basically an image representing the movement between two images. And we feed the last two images of the sequence as optical flow into the loss calculation. So the model is focused with this optical flow loss to focus on the temporal aspect, not only on the shapes. When the model is readily trained, we throw away the flownet and the discriminator parts, and we only need the trained encoder and decoder from the UNet to make predictions. The model then gets frames 1 to n-1 and predicts the follow-up frame. We use the predicted and the ground truth frame afterwards to calculate a peak signal to noise ratio. And this single float metric is later on used as an anomaly score. We have one problem in our situation because an anomaly score is heavily biased by the background. The background contributes too much to the reconstruction error, and we have a static background. One solution to this is to include some kind of attention map in the loss calculation. So we mask the static background and force the loss calculation to focus on the areas the lift seat go through. To generate an attention map, we used something called dynamic images. You see 5 examples at the bottom. A dynamic image is a representation of some video clip where all the frames are represented, including the motion as one image. There is something like a motion blur image, but not exactly that. They are intended to be used as input for trainings, but they also provide a perfect attention map for our purpose. Now let's talk about the more complex cases, the load and unload scenes. Here we need a different approach, action recognition. Simply using binary anomaly detection is not sufficient here. And a lot of papers have been released in the last 2 years. And I read a lot of them, and the approaches can roughly be categorized into these two parts. We have 2D convolutional network architectures that are complemented with a recurrent neural network, like an LSTM. And we have 3D conv networks, where the kernel is extended by one dimension and they can directly process sequences. They all have in common that they provide self-supervised training architectures, where the goal is to predict a future frame again. And sometimes there are 2 streams versions that include optical flow images. Basically, you train 2 types of models, one with RGB input stream, the other with optical flow inputs. You make prediction on both models, and afterwards, you average the prediction result to increase the accuracy. To use the network after self-supervised training, you in both cases need to train some had some classification layer to use it for a downstream task like action recognition. You can also fine-tune the whole model, but in any case, you need to add some dense and softmax layer to get to your predictions. And this is where we need the ground truth data that has been prepared, because this is the supervised training part. We already trained the backbone network with a lot of video data using self-supervised training, and now we use the small portion of labeled data to make a useful model for a use case. We have one thing that we need to overcome. We want to recognize very rare events. Accidents happen only a handful per day. So we need to somehow balance the data that we have, because there is a ratio 1 to 50 in some classes where we have problems to normal, for example. The common answer is to augment the data, but you cannot directly apply what you do with single images to spatiotemporal data. You cannot flip frames, you need to flip all of them. You cannot simply add noise to produce new images, because you cannot augment the temporal aspect. But what you can do is to include a sample weight in the loss calculation during training time. So you try to force the loss function to make more focus on the underrepresented classes. But if you do this too heavily, you get a per label overfitting, and again, your model provides very poor results. So you can do a sample weight to compensate 1 to 10, 1 to 20, but not more. And you need to be creative to sample as much sequences as possible out of your data for the underrepresented classes. Always the data preparation part is the longest and hardest part. It is the same in any AI project. I have some lessons learned during the last few months where we developed the system. There is no known to work well solution or model. You have different approaches, mostly optimized and a solution for some data set that represent some niche of problem task, and you don't have models that simply work well in all kind of use cases. There are many papers that are published, and there's a lot of movement nowadays and a lot of new ideas how we can self-supervise the training. But the best self-supervised training strategy I found is the future frame prediction, and self-supervised training becomes more and more important because perfectly labeled data is rare and becomes more and more unrealistic. The definition of an anomaly is unbound, so labeling is also hard for this reason. And you should use transfer learning whenever you can. Also, when you do self-supervised training, you can use prepared weights and simply initialize your model with them, and you will get better results. This is basically the same that goes for the image classification tasks. We have, all in all, very good results for the action recognition model. We have a training accuracy of 90%, but you need to acknowledge that the field accuracy is even higher because you have a great number of normal classifications there. And we have also very promising results for the anomaly detection model. It's a little bit too early to tell if it really will work well in production, but in the lab, it works very well. We need more testing and inspection of the results, but they are promising. So reconstruction for simple scenes seems to work well, but I cannot make a final judgment yet. At least they are useful to automate pre-curation of clips and, as I said, for the non-complex scenes. We have a beta system out in the wild, and I will show now some result videos where the system itself, you can see it here, is represented by an orange and a red flashing light at the bottom of the image. And the system will alarm in case it detects any dangerous situation. Here we have an employee that cleans the bottom and makes the seats clean and stuff. The system keeps calm. There is no detection of a problem. as expected. But when a crowd of kids runs in, the system sees a problem and would slow down the lift, as been indicated by the orange light here again. So the system learned that kids are a problem if they are too slow and that it needs to slow down the lift. But kids are not always a problem. They're only a problem if they're nearby a lift seat. Here we have a kid that is even falling down, but there is no dangerous situation. So the system, again, keeps calm. And the next one, come on, yes. But here the seat is very nearby and the system, again, alerts and would stop down the lift. I repeat it because it's here where the system alerts. Yeah. Yeah, and these are the first results that we got with our action recognition model. I hope I was able to give you an impression of what you can do with AI and video data. And maybe our team can help with your use case as well. We also have a booth at the datalift 5, so drop us a line. And yes, thank you very much for listening, and I'm looking forward to your questions now.
Yeah, thank you very much, Sebastian. Very interesting talk. So just note, if you have any questions, please send them in the chat. I mean, I guess you can also post in the Q&A, but maybe send them in the chat so I only have one channel to watch. So yeah, it sounds like a very interesting project. And you already mentioned at the beginning that, I mean, it's like how many data, how much video you have there. So it's like, I don't know, 1,000K of data. And so, I mean, you say that because you cannot label everything, it's just too much. You use this self-supervised approach. And I mean, I'm that much with computer vision, but I remember like the one computer vision project I was part of, at some point we needed to sit there and just label frantically lots of images. And I was wondering, so how much do you still need to label if you work with self-supervised, this self-supervised approach? Like how much time you still spend labeling?
Simple answer is most of the time, and this will never stop. It is a bootstrapping process to build up a data set. You start with a few labeled examples that you have. You try to train some network that allows you to do some semi-automatic scanning of new video footage that you get. You use the first results of the model you trained to pick and label some more sequences, and you somehow try to build up on this. So when you manage to get a corpus of labeled data, it is never enough. And the quality is always not sufficient. And these two facts are basically leading you to always come back to the data part of the project. I would say in AI projects, it is very common that in the end, you work most of the time with the data. And even if you have deployed your first version in production, you continue to do so to improve the model. It never stops. It is
yeah, I think it always sounds so glamorous that when outsider, like people not in the industry, think it's like, oh, it's all like the computer learns automatically, and in the end, it's still humans all the time looking at pictures and labeling. Speaking of humans looking at pictures, so how is this system like? So I mean, you still have this. In the demo that you showed, this kind of there's some light. So I assume some person is actually looking at the light. So how is it currently? So currently, I guess it's like, yeah, someone looking at the results of what the machine says. How much will this be automated in the future in terms of supervision, human supervision?
I think the system will not replace the human that supervises the lift, but make him more productive. At the moment, you need one person for each lift entry and unload location. And this person needs to often look at more than one or two displays to supervise more than one lift situation. In this case, our system can alert and put attention to the right spot so the human can react even faster. And I guess there will be always a human in the loop. But the plan is to build a fully automated system. The idea is if you can provide a fully automated system and you put a human using that system onto it, you end up with a very secure solution. And security is the most important thing. So I think the human will never disappear, but at least he will become more, or she will become more productive. And hopefully safety is increased.
Yeah, I mean, I'm not sure if you were at the previous talk by Irina, the interview. So, I mean, this was also one question I thought. So, I mean, they classified this in like the different high risk use cases. And I mean, if I remember correctly, I think this one was not in the European Union, but in America, this Skylift. So I guess it would not be affected by this. But since you're operating also in the European Union, so how do you see these regulations? I think this one, for example, might fall under the high risk AI system as critical because it's like concerns critical infrastructure, or there might be the risk to humans.
It depends on the definition of high risk. I guess the EU means with high risk personal data. So things like Facebook are a big problem. But I don't think that the operational security is in the focus, because the model, the AI in the Pixis AI system only makes predictions. The system is composed of more components. You have parts that get more than one classification and decide if there are the need of directives. You have systems for safetyness, like a panic button to stop the system. So you have safety measurements, but this is like any other big machine has the same things. If you move people and parts, you need to have a panic button somewhere. I guess you cannot talk more about high risk avoidance than having a human stopping the system in a complex situation where the machine does not react correctly. I cannot imagine how the EU can help me with some regulations or guide me through this process. It needs to be as safe as possible. It's hard to define and to specify what is meant in our case. But I can really perfectly understand what the EU is trying to do when it comes to the personal data. And this is a very important topic, because when you exploit human data, you in the end exploit the humans. And this should not happen.
Yeah, I mean, I think I personally also welcome the regulation they had. I remember there was big discussion when it was first leaked. I mean, I think the way you describe your system to me, it also seems very safe in the sense that there is still this human in the loop. I do wonder if maybe some other people might want to think or have this idea that you could fully automate it without human. I think this is kind of where this regulation by the European Union also would hold and say, no, we need to regulate if the AI makes actually decisions about that could concern or harm humans by like stopping or not stopping the system. But yeah, I think also like very valuable.
Yeah? I'm not sure if the politics will regulate this, but I'm quite sure the insurance will. The insurance for sure enforces a human in the loop simply because they will not pay otherwise. And I think this will have more impact into how AI systems are built than the politics, at least in the USA.
Okay, very interesting point. I didn't think about this yet, but makes sense. If there's money involved, money will also regulate.
Yes.
So I don't have any more questions. So I don't know if there's no more questions from the audience. I think, then we are already at the end of the session. Looking at the program, I think the next in the program is that there's still the expo where you can, I'm not sure, are you also at the expo, Sebastian?
Yes, I will stick there.
Okay, so if you want to talk to Sebastian, you can also go to the expo and probably see him there and talk what the company pixolution does. There's also still...
Thank you very much. It was a pleasure.